So, welcome to lecture series on advanced linear algebra. Today we will discuss about the applications of primary decomposition theorems in different domain. Last time we are discussing about the applications in solving initial order problems. We have defined the concept of generalized eigenvector of specific rank and how it introduces linearly independent vectors. So, in continuation of that, so let me again consider a system of equations autonomous system, please. X dash is equal to Ax, dx by dt equal to x dash is equal to Ax, please. Let A is a 6 cross 6 matrix over the field capital F, and its characteristic polynomial Fx is equal to say x minus lambda 1 whole square and x minus lambda 2 power 4, where lambda 1 and lambda 2 are distinct scalars. Let the minimal polynomial of A be say x minus lambda 1 into x minus lambda 2 power 3. Then we know the solution of x dash equal to Ax depends on eigen value and eigenvectors as well as generalized eigenvector. Since minimal polynomial, the factor x minus lambda 1 is a linear of first degree. So, certainly if I consider A minus lambda 1 I, this matrix will have definitely rank as a 4. So, that null space dimension of the null space will be 2. So, that I will have 2 linearly eigenvectors associated to lambda equal to lambda 1. So, in that case one can find 2 linearly independent solution of the system x dash equal to Ax associated to eigenvalue lambda equal to lambda 1. But in the case of lambda 2, I see that characteristic polynomial is having the factor x minus lambda 2 power 4, whereas minimal polynomial having factor x minus lambda 2 power 3. So, definitely I will have the eigenvectors associated to lambda equal to lambda 2 if I consider, then A minus lambda 2 I, certainly I will have rank will be also again 4. So, that I will have 2 linearly independent eigenvector, please. Since matrix is 6 by 6, already obtained 2 linear independent eigenvector associated to lambda equal to lambda 1, already obtained 2 linear independent eigenvectors associated to lambda equal to lambda 2, So, still we need 2 more. These 2 more linearly independent vectors will be obtained from the, I will have a vector in the null space of A minus lambda 2 power 3. There will be vector in that null space of rank 3, which will give me 3 linearly independent vectors. Out of 3, 1 will be eigenvectors, which is basically already calculated. So, I will have 2 more vectors which are linearly independent also. So, altogether I will have 6 linearly independent eigenvectors, and one can calculate the corresponding complete solution, please. So, if I have a minimal polynomial like x minus lambda to power 3, we are 100% sure there will be a vector in the null space of A minus lambda 2 power 3, say V 3, such that A minus lambda 2 operating on V 3 equal to 0, but A minus lambda 2 I square operating on V 3 is not equal to 0. So, I will have a chain of generalized eigenvectors, please. Now, suppose these vectors are known, how to find the solutions associated to this generalized eigenvector V1, V2, V3, or if I consider rank is R, then V1, V2, Vr, please. Now, let me answer these questions. Solution associated to a generalized eigenvector of rank are associated to eigenvalue lambda of the matrix A. So, let U be a generalized eigenvector of rank R associated to eigenvalue lambda of A. So, it gives R linearly independent vectors, generalized eigenvectors basically V1, V2 and say Vr. Vr I am denoting as a U, please. We know Vr equal to U equal to A minus lambda I power 0 operating on y, and Vr minus 1 is equal to A minus lambda I Vr, and in general we have written that Vi minus 1 is equal to A minus lambda I Vi, okay, and calculated V1 will be equal to A minus lambda I operating this one, and 0 is equal to A minus lambda I operating on V1. This is already seen it. Construct the R functions as below. So, let me define R function. That first x1 I am defining as e to the power lambda t into V1, and x2 is equal to e to the power lambda t into t V1 plus V2, x3 is equal to e to the power lambda t into t square V1 plus t V2 plus V3, and general x r I am denoting as e to the power lambda t to the power r minus 1 V1 plus t to the power r minus 2 V2 plus t into V r minus 1 plus Vr. So, I can say in general capital Xj equal to e to the power lambda t into sigma t to the power j minus I and V I equal to 1 to j. I can say that x j is equal to e to the power lambda t into t to the power sigma t to the power j minus I into V I. So, I have constructed this is a some R functions like this. Claim x1, x2, xr are linearly independent solutions of the system dx by dt equal to Ax. So, let me first prove that each of them are the solution of this system please. So, we have xj equal to e to the power lambda t into summation of I equal to 1 to j t to the power j minus I by, I did mistake in my construction please, x3 is equal to I am defining it here factorial 2, and so it is factorial r minus 1 and this is factorial r minus 2 and so on please. So, I need a factorial j minus I please. Okay. So, I am defining the R functions like this. Okay. So, I have defined that x j is equal to e to the power lambda t summation I equal to 1 to j t to the power j minus I by j minus I factorial into V I please. So, dxj by dt will be equal to how much? This will be equal to e to the power lambda t into sigma I equal to 1 to j minus 1 j minus I into t to the power j minus I minus 1 divided by j minus I into j minus I minus 1 factorial into V I plus I will have lambda times e to the power lambda t into sigma I equal to 1 to j t to the power j minus I by j minus I factorial and V I. So, I have dx by dt equal to this quantity. So, let me write down this is equation number 1. Now, xj will be solution provided satisfied. So, dx by dt must be equal to a into xj. So, we need dxj by dt must be equal to a xj. So, this implies your Axj is equal to how much? This is equal to A into e to the power lambda t into sigma I equal to 1 to j and t to the power j minus I by j minus I factorial and Vi. So, this can be written as e to the power lambda t is a scalar quantity, take it out and I can bring the matrix inside the summations. So, t to the power j minus I by j minus I factorial into AVI. So, I have Axj is equal to like this is my second equation please. Okay, we have Vi minus 1 equal to A minus lambda I Vi. So, AVI equal to lambda I Vi. So, I can use that relations here also. So, this is equal to e to the power lambda t into sigma t to the power j minus I by j minus I factorial. According to previous formula, we have AVI equal to lambda into V I and plus Vi minus 1. So, I can substitute this equal lambda Vi plus Vi minus 1. Okay. This is equal to lambda Vi plus Vi minus 1. Okay. So, this is equal to e to the power lambda t into, I can take it out lambda common, sigma, this is I equal to 1 to j please. So, I equal to 1 to j, I will have t to the power j minus I by j minus I factorial into Vi, and other one I will have e to the power lambda t into sigma t to the power j minus I by j minus I factorial I equal to 1 to j Vi minus 1 Vi minus 1. So, Axj equal to lambda e to the power lambda t sigma I equal to 1 to j t to the power j minus I by j minus I factorial and Vi plus e to the power lambda t into sigma I equal to 1 to j t to the power j minus I by j minus I factorial and Vi minus 1. So, this is equal to this plus I can say e to the power lambda t when I is replaced by I minus 1, I is replaced by I minus 1. So, then I will have this is equal to sigma 1 to j minus 1 and I will have t to the power j minus I minus 1. I am replacing I equal to I plus 1. So, that it will be is going to be 1 to j minus I and then denominator will be j minus I minus 1 factorial and I minus 1 is equal to I means it will be Vi. So, this is nothing already obtained by 1 is equal to dxj by dt. So, each xj t satisfies the governing equations and also we will see that at t equal to 0 it satisfied the also initial conditions, then I will having one linearly independent solution also. So, we already checked that this V1, V2, V are linearly independent and we have also n linearly independent solution, therefore, x1, x2, xr will be also linearly independent. Since xj0 j equal to 1 to r are linearly independent. So, each xj is also linearly independent. So, I have r linearly independent solutions of the systems Ax dx by dt equal to Ax, where we have a generalized eigenvector of rank R. So, we see that the primary decomposition theorems is used here to find the solution of the initial value problems dx by dt equal to Ax when system is autonomous case. Now, let me go the applications of primary decomposition theorems in some other cases. Application of primary decomposition theorems PDT in other cases. Okay. We have seen if T is a linear operator on a finite dimensional vector space, then T can be written as sum of a nilpotent operator plus a diagonalizable operator D. T can be written as n plus D. This is we have obtained from the primary decomposition theorems when the minimal polynomial of T is product of linear factors. I mean to say, when the field over which the vector space V is defined is algebraically closed, then we are safe. So, you can say that in that case any operator defined over the finite dimensional space certainly will have decomposition of the form of n plus d, where n is a nilpotent operator, and this is a diagonalizable operator, please. Okay. So, that we have already seen. Let me introduce some specific type of operator or matrix. We will show that this is a nilpotent operator will also have block diagonal forms. Their element will be some specific structure, please. So, we are going to talk about that issue. So, before that, let me introduce some terminology. First is Jordan nilpotent block. Consider a matrix N defined by n equal to 0, 1, 0, 0, 0, 0, 1, 0. So, the diagonal entries are 0, super diagonal entries are 1. Okay, super diagonal is 1. So, I have defined a matrix like this. So, consider matrix N of say R cross R order defined by like this thing, where N is a R cross R matrix whose super diagonal entries are 1 and rest are 0. So, we will see that this n I am writing as a basically n of r, I mean this is a nilpotent operator or nilpotent matrix of index r, is a nilpotent matrix of index r please. That is n to the power r equal to 0, but n to the power r minus 1 not equal to 0 please. See, the way I have written the matrix n, I can immediately construct a linear operator over say f r cross 1 like this. We can define a linear transformation say T from f r cross 1 to f r cross 1. I am defining like say E r which is equal to 0 0 1 goes to 0 0 0 1 0, that is equal to E r minus 1. If I defined the map which is mapping E r to E r minus 1, I mean to say T of E I equal to E I minus 1. If I consider E 1, E 2, E r a standard order basis in over the vector space f r cross 1, then I am defining this one please. This implies that T of E r equal to E r minus 1, T square of E r is equal to E r minus 2, and T to the power r minus 1 operating on E r will be equal to E 1, and T to the power r operating on E r equal to 0 vector please. So, if I write the corresponding matrix representations with respect to this standard order basis, I will get the matrix representation is basically your capital N, which you can say it, because the E 1 goes to 0, E 2 goes to E 1, so like this please. Okay. So, this implies for B equal to E 1, E 2, E r order basis, the matrix representation of T with respect to order basis B will be equal to capital N, or I have written here N r please for the same place. So, we see that this Jordan nilpotent block defined of index r defined like this is basically coming as a consequence of the shifting operator T from f r cross 1 to f r cross 1 defined by E I goes to E I minus 1. So, that way please. And let me also define another matrix that is called Jordan block. Jordan block associated to an eigenvalue lambda. Let me define these ones. The Jordan block associated to an eigenvalue lambda, I am defining like this J lambda. It is basically, again it is a square matrix say of order r cross r, then I am defining here it is basically lambda times I is an r cross r identity matrix plus nr. Nr is Jordan nilpotent block matrix Nr of index r. So, n to the power r equal to 0, but n to the power r minus 1 not equal to 0, and the n having structure like what I have already done, that except super diagonal terms where all each super diagonal term is equal to 1, rest of the terms are equal to 0. I am defining another matrix called Jordan block of say order r cross r as J lambda associated to eigenvalue lambda as lambda times I is basically r cross r matrix identity matrix plus nr please. So, this means that this will be equal to something like this please, your lambda 1 0, 0. So, all the diagonal matrix will be lambda, super diagonal is 1. So, rest are 0. So, I will have like 1 1 1 like this and 0 is here. So, this is my Jordan block associated to eigenvalue lambda place. Okay. So, based on these definitions of the Jordan block associated to eigenvalue lambda and Jordan nilpotent block n, let me also use one theorems related to the nilpotent operator or nilpotent matrix of index R. If you consider, then there is a classical results that if n is a nilpotent operator of index R, then this nilpotent operator have a block diagonal matrix representations, where the diagonal entries will be Jordan nilpotent matrix of different index please. So, let me state about the theorem please. Let n be a nilpotent operator of index say k. Then n has a block diagonal matrix representation where each diagonal entry is a Jordan nilpotent matrix, the Jordan nilpotent matrix. There is at least one Jordan nilpotent matrix of either index or order, we can say here, of index, because nilpotent Jordan nilpotent is basically index k means definitely it has to be of order also, I mean k by k please, of order k, matrix of index k or order k please. All other entries will be Jordan nilpotent matrix of, I can say index not to confuse, of index less than or equal to k. The total number of Jordan nilpotent matrix will be uniquely determined by the operator n or matrix n, both are same. If you consider any of the operators, fine. If you consider matrix, then it is also fine. So, this is basically a classical theorems which talk about the block diagonal matrix representation of any nilpotent operators or nilpotent matrix of specific index k. In fact, the number of Jordan nilpotent matrix of specific index or order is uniquely determined by the number two m I minus m I plus 1 plus m I minus 1. So, the number will be 2 m I minus m I plus 1 plus m minus 1, where m I is the dimension of null space of the n to the power I. So, this is the classical results. The proof is bit lengthy, that is true. Right now, I shall use these results to give a Jordan canonical representation of a operators when the operator is defined over the vector space, which is also defined over the field, and field is algebraically closed. So, using these results and using the previous results, that when you consider linear operator defined over a finite dimensional space, that operator can be written as a sum of a diagonal matrix and a nilpotent matrix. And using that previous result, that every nilpotent operator will have a diagonal representations, block diagonal representations, where each entry will be basically Jordan nilpotent matrix space. So, based on that, let me give a talk about theorems called Jordan canonical representation theorems. Jordan canonical representation theorem. Jordan canonical representation theorem says that let T be a linear operator on a finite dimensional vector space V over the field say capital F. Let Fx equal to x minus c1 power n1, x minus c2 power n2, x minus ck power nk, and px equal to x minus c1 power say m1 to x minus ck power mk be the characteristic and minimal polynomials of T. So, I have considered Fx as a characteristic polynomial and Px is the minimal polynomial of the operator T. So, that polynomials are factorizable over the field, that is given. Then T has a block diagonal representations. Representation say J such that each diagonal entry geometry is a Jordan block, something like J lambda. Along with first, for each eigenvalue lambda I, there will be at least one Jordan block of order mi. That is basically the power of x minus ci in the minimal polynomials, and all others blocks will be of order less than or equal to mi. Second, sum of all order of j I j lambda I must be equal to ni, that is algebraic multiplicity of the eigenvalue lambda I. So, it will be okay, I have written Ci, so it will be sorry, then Ci please, not J. I should write Ci. Okay. So, sum of all order of Jij must be equal to Ni, that is algebraic multiplicity of the eigenvalue Ci. Third, the number of Jordan block associated to eigenvalue lambda I must be equal to geometric multiplicity of eigenvalue lambda I. Fourth one, the total number of Jordan block will be decided uniquely by the operator T. So, this is called Jordan canonical representation theorems. He is saying that if T be a linear operator on a finite dimensional vector space, when the characteristic polynomial or minimal polynomial are factorizable over the field, then the operator T will have a block diagonal matrix representation J, where the diagonal entries will satisfy these four hypotheses, I mean 4 condition please. That first, for each eigenvalue Ci there will be at least one Jordan block Ji j Ci of order mi, and all other will be of order less than or equal to mi. Second, sum of all order of Jij related to eigenvalue Ci must be equal to geometric multiplicity of the eigenvalue Ci, that is must be equal to Ni. Third, the number of Jordan block associated to eigenvalue lambda I, sorry it will be Ci please, must be equal to geometric multiplicity of eigenvalue Ci please, and the total number of Jordan block will be decided uniquely by the operator T please. So, let me take an examples. Let T be a linear operator whose characteristic polynomial fx is equal to say x minus 1 to the power say 3 into x minus 2 to the power say 4, and minimal polynomial px equal to say x minus 1 to the power 3 and x minus 2 to the power 2. Then write down the all possible Jordan form of the operator T. So, Jordan form will be like this, one is like this, j equal to I can say diagonals. First will be since the minimal polynomial is px equal to x minus 1 to the power 3, and in characteristic polynomial also I mean there x minus 1 to the power 3 that is there. So, 1 is will be 1, then Jordan block to lambda and 1. So, 1 1 0 0 1 1 0 0 1. So, one entry will be like this associated to the eigenvalue equal to 1. Then second entry associated to the eigenvalue lambda equal to 2, the Jordan block will be at least one will be of order 2. So, order 2 means I can write down like 2 and 1 0 and 2. So, other ones it may be of order 2 as well as order 1 also, because 2 plus 2 is equal to 4, that is basically the algebraic multiplicity of the eigenvalue 2. So, it may be 1 is like this 2 1 0 2. So, this is one possible Jordan block diagonal representation I mean Jordan form. Say another one is diagonals. The first one associated to eigenvalue 1, it will be always here in this case a Jordan block of order 3. So, eigenvalue 1 1 0 0 1 1 0 0 1, this entry will be there. Second entry will be 2 1 0 2, then Jordan block of order 1 also. So, I have only 2 possibilities here, but friends, if it is given that the geometric multiplicity of eigenvalue lambda equal to 2 is exactly equal to say 2, then I will have only first option. If it is 3, then I will go for the third option. Is it possible to have geometric multiplicity of eigenvalue lambda equal to 2 as a 4? No, otherwise minimal polynomial will be x minus 1 whole q into x minus 2. So, this is the simplified form of the corresponding operator T, which is defined over a finite dimensional space. Here I have taken say F7, then I have the Jordan form is like this. So, we will continue this applications for other situation also.